Hi everyone, I'm Yanbo Pan, and I'm a first-year PhD student at the University of Virginia. I'm also associate with the Cosmic AI Institute. Today, I'm happy to share with you the work that we have been doing in trying to use statistics and machine learning to inform observers about their next optimal observation windows for their radial velocity measurements. To start with, radial velocities are everywhere in astronomy. In astronomy, usually there are two bodies that are interacting with each other via gravitational effects. And for observers, we would usually observe it along our line of sight. As light travels through the stellar atmosphere, because of the unique chemistry in the atmosphere, it will create characteristic absorption features. And by observing the shifts in the wavelengths of all these features, we can see the wobbling motions of these stars. So here I'm showing a binary star systems which have more than 40 observations called S1040 in an open cluster M67, and we can fit a very reliable velocity curve through these data points. And it can teach us a lot about interesting features, physical parameters for these systems. For example, its period, eccentricities, velocity amplitude, etc. Using that, it can teach us about the actual physical separations of the two bodies as well as its mass ratios. In many cases, we don't have ample number of data points. In many cases, we only have 3 to 5 observations for binary stars. So a lot of people have been developing binary system orbital solvers like this. Here I'm showing a binary orbital solver called the TheJoker, which stands for Johannes Kepler. And this is essentially a Monte Carlo rejection sampling for a two-body problem. Adrian Price-Williams developed it in 2017 and has built our understanding of how binary stars behave in this model. Not surprisingly, as we add more observations to our data points, on the left, when we are only having 3 data points, we can fit many more possible posterior orbits through these data points with close to 0 chi-square essentially. When we are adding data points, we can constrain orbits much better with better informed physical properties. However, all these new observations, they are not free, as shown on the right. They are costly for people to write observing proposals, and we need budgets to use some of the best telescopes in the world. So for people who are interested in faint stars in distant galaxies outside the Milky Ways, stellar spectrums can be expensive to obtain using some of the largest telescopes in the world. Like the Large Binocular Telescope with 2 8-meter class mirrors can give us spectrums with signal-to-noise ratios high enough to obtain radial velocity from. So this begets a question that how many radial velocities are needed to constrain all these binary stars in orbits, and if we can push the limit further using some smart observing strategies to reduce the number of observations needed for this problem. This motivates us to design a tool called HARLEE, which stands for Helper for Analyzing Radial Velocities with Limited Epochs and Error. So here I'm showing a prototype of the tools that I'm currently developing. On the upper panel, I'm showing a system which we only have 4 observations of. Using TheJoker that we can generate some possible posterior orbits that can fit through these data points quite well. In the past, we usually stop at this point and saying these orbits are degenerate, and that's usually the case. However, using these tools that we are developing, we are converting these posterior orbits showing in these colorful curves into priors for our future observations. So by calculating in each future observing time, we are calculating to the first order variance of these predicted radial velocities and it can output times where it can help observers to constrain orbits most well. Usually in the time where we would predict there might be a periastron approaches towards us with a very high velocity amplitude. So on the bottom panel, when we are implementing these algorithms, that we can constrain the orbit quite well with only 9 data points. I want to stress that this is only preliminary work, and we want to test it on a wide sample of binaries with different period and eccentricities and velocity amplitude, and we hope this tool can be useful to the field in general, for example, for binary stars as well as for exoplanets. I'm also going to present this work in the Cosmic AI conferences happening in this July. So lastly, as a summary, radial velocities are everywhere in astronomy, and they are useful tools for us to learn about binary stars as well as any other two-body systems. However, all these status spectrum radial velocities are costly to obtain for faint sources, so we can use existing observations to inform about our future observations. That's all. Thank you very much for your attention and time, and I look forward to feedback.